The turbulent surface of our Sun radiates energy powered by a single continuous reaction, the fusion of two protons. Standard electroweak gauge theory models this process with high precision. It calculates reaction rates and neutrino fluxes by treating the fusion as an instantaneous particle creation event. But this standard model operates entirely on Feynman diagrams and mathematical operators. It offers no continuous physical geometry to describe how two objects actually approach, intersect, and merge in space. Physicist Boris Kriger proposes a framework that addresses this limitation. He models the proton-proton fusion event as a continuous topological deformation. This interpretation suggests the merger of two microscopic protons into a deuteron is structurally parallel to the macroscopic merger of binary black holes. Across both scales, two topologically closed objects merge into one. Any structural excess that cannot be accommodated with a new shape is radiated away as perturbations of the surrounding substrate. To understand the weak nuclear force in this context, we must examine the mathematical topology of the chiral field. We begin at the microscopic scale, defining the nucleon within the Skyrme picture of quantum chromodynamics. In this framework, the proton manifests as a topological soliton, a stable, twisted knot within the continuous chiral field. This diagram visualizes the specific geometry of that knot. We model the isolated proton as a unit radius hypersphere, an S3 configuration embedded in four-dimensional space. The degree of this outward vector map defines the proton's topological charge, representing a strictly conserved baryon number of 1. The most critical property of this geometry is its topological closure. The sphere is entirely self-contained, and this closure is the physical source of the proton's immense stability. Because of disclosure, any continuous deformation to the shape preserves the topological charge, ensuring the local energy density stays below the confinement limit of the strong force. When two protons approach each other, they interact mathematically like two completely closed, impenetrable universes about to touch. As the distance between the centers of these two S3 configurations shrinks, they must negotiate their overlap. Their collision geometry is strictly governed by the rotation group of four-dimensional space, mathematically known as SO4. The SO4 group decomposes into two independent rotation factors, a left factor and a right factor. This introduces the core structural primitive of the fusion merger, counter-rotation. One proton rotates through the left group, while the other rotates through the right group. If both spheres rotated in the same direction, their mathematical intersection would be a generic, highly unstable sphere. Counter-rotation prevents this instability. The opposing spins force the geometric intersection of the two spheres to become a torus. The kinematic spin of approaching protons is dictated by four-dimensional geometry, creating a donut-shaped scaffold for the new nucleus. The counter-rotating protons soon reach a critical separation distance where their boundaries overlap. The topological closure of the constituent protons is never violently disrupted. The ambient field deforms continuously, without breaking or triggering local deconfinement. Mathematicians call this a Heegard splitting, a method of building complex three-dimensional manifolds by gluing simpler shapes together along a shared boundary. This schematic visualizes that exact boundary condition. Where the two protons intersect, they form a specific coordinate constraint called a Clifford torus. Each original proton effectively acts as a solid torus, and they seamlessly glue themselves to either side of this shared Clifford torus boundary. The result is a single closed configuration with a donut-shaped toroidal symmetry. The original topological charges have merged. The baryon number of this new system is now 2. We have built a deuteron. While standard physics identifies this as a nuclear bound state, the topological view describes a configuration assembled continuously via Heegard gluing in four-dimensional space. There is a paradox inside this newly formed toroidal deuteron. The shape is complete, but it faces a structural incompatibility with its initial ingredients. Because the two initial protons were identical, their internal vector fields, their isospin orientations, arrived perfectly parallel to each other. But the target B equals 2 Skyrme configuration mathematically dictates that its two halves must have anti-parallel chiral orientations to maintain stability. To resolve this, One of the two halves must structurally reorient itself, forcefully flipping its internal chirality from an up-quark state to a down-quark state. This purely geometric reorientation is the structural equivalent of the Standard Model's weak nuclear interaction. The violent geometric flip creates a structural excess. The conserved charge and lepton numbers from the original proton no longer fit inside the stable torus. This excess must be forcefully ejected into the surrounding environment. This radiation manifests as sigma perturbations of the QCD vacuum, rippling outward from the merger site. We detect these highly specific sigma perturbations in our laboratories as a positron and an electron neutrino. The weak interaction is a mandatory topological exhaust system required by geometry to stabilize the fusion of two perfectly closed shapes. The continuous topological deformation of two protons mirrors the structural mechanics observed in binary black hole mergers. This split-screen chart illustrates the mechanical parallel. For black holes, the substrate is the spacetime metric, and the radiated excess is mass energy in the form of gravitational waves. For fusing protons, the substrate is the chiral sigma QCD vacuum, and the radiated excess is charge and lepton numbers in the form of positrons and neutrinos. This structural framework is empirically conservative. It aligns with the established calculations and astrophysical data formulated by physicists like Hans Bethe. The predicted kinetic energy of the radiated sigma perturbations matches the established 0.42 MeV Q value for proton-proton fusion. Macroscopic topological substrate radiation is already an observed reality, continuously measured by gravitational observatories. Whether observing the collapse of stellar mass black holes or the fusion of hydrogen in the Sun, counter-rotation and substrate radiation act as the universal structural primitives of our physical reality. As we map the universe from the scale of galaxy clusters down to the atomic level, we reach the scale where matter first organizes itself into stable nuclear structures. Here, the specific laws governing the assembly of the elements are locked into place. The standard historical framework for how the universe built its elements relies on Big Bang nucleosynthesis and the sequence of stellar burning mapped out in the mid-20th century. This chart shows the standard cosmic abundance curve, tracking binding energy per nucleon against mass number. Standard reaction networks accurately describe three major empirical landmarks here: the mass fraction of primordial helium holding steady at roughly 25%, the spite plateau for lithium-7, and the energetic peak at nickel-62 and iron-56. The data fits. But standard models treat essential structural gateways, like the complete absence of stable nuclei at mass 5 and mass 8, or the highly specific energy level required to synthesize carbon, as numerical accidents of nuclear potential wells. Phenomenological models accurately tally particle collisions to tell us what happens in the cosmos. But to understand why the periodic table possesses this exact structure, we have to look past collision statistics and examine the underlying geometry. Paper 16 in this series proposes an alternative. Cosmic nucleosynthesis is a sequential cascade through a distinct phase space of accessible, closed multibaryon topologies. Instead of viewing nuclear reactions as two-body point particles colliding in a void, we can map them as three-dimensional structural geometries locking together. The engine driving this cascade is structural coherence-energy. Matter naturally flows toward configurations with higher point group symmetry. As shapes become more symmetrical, they release energy. This geometric flow divides cosmic history into two distinct thermodynamic phases. Phase 1 is topological absorption, driving matter upward in symmetry until it hits the iron peak. Phase 2 is topological rearrangement, which governs the formation of the heavy trans-iron elements. By applying strict rules of geometric symmetry to this topological cascade, we can mathematically derive the entire cosmic abundance curve from first principles. During the first 3 minutes of cosmic time, the universe rapidly expanded and cooled. At roughly 0.8 mega-electron volts, weak force interactions froze out, locking in the starting ratio of protons to neutrons. Structurally, the proton and neutron are identical spherical hedgehog topologies, differing only in internal charge. In Phase 1's first step, they merge, deforming into a single toroidal ring, a deuterium nucleus. This more symmetric closure releases coherence energy. But the early universe was flooded with high-energy photons. Until the ambient cosmic temperature dropped below 80 kiloelectronvolts, that external photon heat easily overpowered the internal structural coherence of the deuterium toroid, breaking it apart as fast as it formed. This is the deuterium bottleneck. Nucleosynthesis could only proceed once the universe cooled enough for structural geometry to achieve stability against ambient cosmic heat. Once the bottleneck broke, assembly rapidly resumed. 2 and 3 baryon structures quickly merged to form 4 baryon closures. This brings the cascade to helium-4, the first hypersymmetric closure. It forms a perfect cubic topology, granting a massive coherence advantage. Because of this, almost all available neutrons were absorbed into these stable cubic closures, dictating a 25% primordial helium mass fraction. But immediately after helium-4, the geometric assembly hits a physical wall. There is no stable nucleus with 5 baryons. A 5-baryon topology forces the structure out of its cubic symmetry into a non-hypersymmetric, geometrically frustrated shape. It inherently lacks the rotational stability required to maintain closure, so it fractures. The mass 5 gap functions as a hard geometrical impossibility within the closure space. Lacking the symmetry required for stability, these configurations fracture before they can accumulate, forcing the BBN cascade to halt. The cascade paused until millions of years later. Then, gravitational pressure inside the first stars provided the extreme density required to restart the geometric assembly. As stars fuse helium, they encounter the mass 8 instability.